We're going to be using an app, and here's the app's address up here. You can also get to it on Canvas on the Chapter 9 Notes and Videos page. There's a link to the Power and Type 1 and Type 2 errors applet. So we're going to explore the ideas of Type 1 and Type 2 errors and power. So right now we are going to assume that we have a distribution where P is equal, our null hypothesis value, which is P naught, P sub 0, is 0.5, and we're going to assume that that is actually the true value of P. So in other words, rejecting the null hypothesis would be wrong. So what is the probability, though, that we would get a sample that would cause us to reject the null hypothesis even though it's true? That is known as a type 1 error. Well, the type 1 error has the probability alpha. Alpha is the percentage in this tail region, which we would call a rejection region. In other words, if I got a sample p hat that fell somewhere to the right of this line, then it would be far enough away, less than a 5% probability of happening, that I would reject the null hypothesis. And in this case, that would be an error because the null hypothesis is true. So let's go back to the notes and just summarize. Well, actually, let me look at a couple other things. Go back to the notes and look at that. So type 1 error is rejecting the null hypothesis when it's really true. The probability of a type 1 error is alpha. That is the area of the rejection region. If the p hat is in here, we're going to reject the null hypothesis. Okay, so let's go back to the applet and look at a type 2 error now. Now, a type 2 error occurs when the null hypothesis is really false, but we fail to reject it. So I'm going to set up we're going to set up that the true value of p hat is really 0.7 here. Okay, let me turn off my type 1 error. Okay, so we see here that the true value for p hat is 0.7. The hypothesized value is 0.5. You can see there's quite a bit of overlapping here where a p hat could plausibly come from either distribution. So if I get a p hat in here, how do I know whether it came from the 50% or from the 70% or maybe something in between? So it could have come from either distribution. So what is the type 2 error? The type 2 error is the probability that I will fail to reject the null hypothesis when it's really false. So if I get, so I'm going to put the type 1 error back in here. If I have a p hat that falls into this little red region, I'm going to reject the null hypothesis. And then in this case, that's a good decision because it's false. But if I get a value that falls in this blue region, somewhere between like 0.65 on down, then that value could plausibly have come from this distribution. And it's not in the rejection region. So when I get a value that's right here in this blue area, I'm not going to reject the null hypothesis even though it's false. Even though that p hat really came from this distribution, I can't tell the difference because they're overlapping right here. So that is a type 2 error. So going back to our notes, the type 2 error is failing to reject the null hypothesis when it's really false. The probability of a type 2 error is called beta, and that is the area under this region that is shaded here. If the p hat is in here, it's not extreme enough to reject the null hypothesis, even though the null hypothesis is wrong. Okay, the next thing we're going to look at is a concept called power. Now, power is the complement of the type 2 error. So in other words, if this has a probability of beta, this has a probability of 1 minus beta. Power is the probability that given a certain true value of p, I will correctly reject the null hypothesis when it's false. So that is a good thing. It's good to have power. We want a test to be powerful. We want a test to correctly detect a false null hypothesis. So here we have a 72% chance of correctly detecting the false null hypothesis. Notice that the dividing line for power is the same for the dividing line for the type 1 error because the type 1 error is rejecting the null hypothesis when it's actually true, and power is rejecting the null hypothesis when it's actually false. In both cases, we're going to reject the null hypothesis if I get a sample proportion that is bigger than this line. In one case, it would be a wrong decision if this were really true, if the red distribution were really true. But if the blue distribution were really true, then it would be a good decision, and that's power. So summing that up, the probability that I will correctly reject a false null hypothesis. Okay, and that is given a particular true. So given, given a specific true P. So the probability, this power does depend on what the true P is. If we move the true P, then the power will change. So it is dependent on a specific true P. I want a test to have power. It's a good thing. So the probability of the probability of the power associated with power is the complement of the probability associated with the type 1 error. They are, so if this were, say, 30%, this would be 70%. Okay, last terminology I want to talk about is effect size. Effect size is the difference between the actual probability and the hypothesized probability. So notice that if I were to make that difference bigger, if the effect size were bigger, that power increases because it is easier to detect the difference between the true and the false when they are far apart. If they are close together, it is very difficult to detect the difference because there's so much overlap. So effect size, so notice how power has gone down, but when we increase effect size, power goes up greatly. So the effect size is the difference between the null hypothesis P sub 0 and the actual P. Now, how do these things affect each other? Okay, so we're going to look at a couple things. What happens when we decrease alpha? So let's go back to kind of our, say that our null hypothesis really is true. Okay, and we're looking just at the probability of a type 1 error. So how do we decrease the probability of a type 1 error? Well, we decrease alpha. If we decrease alpha, then the area of the rejection region becomes smaller. In other words, it becomes more difficult to reject the null hypothesis. So if it's more difficult to reject the null hypothesis, then of course it's difficult to make a mistake in rejecting the null hypothesis. Now, how does that affect a type 2 error in power? So if we put in type 2 error in power here, and we create another, fake one here. So here's my 5%. Okay. Now notice we have 5% type 1 error, 28% type 2 error, 72% power. If I decrease the probability of a type 1 error, notice that power also decreases, because if I'm less likely to reject a false null hypothesis, less likely to reject a true null hypothesis, I'm also less likely to reject a false null hypothesis. So power decreases when the type 1 error decreases, and type 2 error, since it is the complement of power, will increase. Okay, so let's look at a couple other things. Actually, let's go back, and so that's why this, if we decrease alpha, which means we're less likely to reject the null hypothesis, both the type 1 and power decrease, because that means we are less likely to reject the null hypothesis whether it is true or false. If we increase alpha, then type 1 and power both increase, because we are more likely to reject the null hypothesis whether rightly or wrongly. The power would increase and type 2 error would decrease. Now let's take a look at the effect size. If we change the effect size, how are things changed? Notice, let me make the type 1 error back to 5% here. Okay, notice the probability of the type 1 error does not change with effect size. It's still 5%. But power increases with effect size and type 2 error decreases. Well, that makes sense, because with a less overlap between the distributions, then I'm more likely to correctly detect a false null hypothesis as that distance increases. So increasing the effect size increases power, decreases the probability of a type 2 error, has no effect on a type 1 error, because that has nothing to do with the false, with the null hypothesis being false. It has to do with the null hypothesis being true. So a larger effect size, no change in type 1 error, decreases type 2, increases power. Sample size, I'm not sure if we looked at that already. So let's say we're pretty close together here with our null and alternate hypothesis, but if I increase the sample size, notice increasing the sample size decreases the variability in the two distributions and makes them not overlap as much. And when they don't overlap as much, that increases the power and decreases the type 2 error, just like increasing the effect size. So when the effect size is small, it's good to increase the sample size so I can see the difference more clearly. So decreasing the sample sizes decreases the variability in the two distributions. Type 1 doesn't affect type 1 error, but decreases the type 2 error and increases power. So in general, if the probability of a type 1 error increases, type 2 decreases and power increases. So power and type 1 go together in that regard. There are 3 ways to increase power. Increase alpha, have a larger effect size, or increase the sample size. So we're going to look at a few example questions now that deal with these concepts. So here's the scenario. Let's say I want to find out if the majority of Covenant students wait until Sunday to do their homework for Monday. I decide to do a random poll of 30 students to find out. P would be the proportion who do their homework on Sunday. Okay, so my null hypothesis would be P is 0.5, and the alternate would be P is greater than 0.5, and I'm going to use an alpha level of 5%. First question. Let's say only 50% of students actually wait until Sunday to do homework. What's the probability that my sample proportion will cause me to reject the null hypothesis falsely and conclude that the proportion is greater than 50%? And what type of error is that? Well, that is a type 1 error. That's rejecting the null hypothesis when it's really true. And it's going to happen 5% of the time because I've set my alpha level at 5%. In other words, if my sample statistic falls in this 5% region, saying that my sample statistic is far enough away from the 0.5 that I'm going to reject the null hypothesis, that's only going to happen 5% of the time. Question 2. Let's say that the actual proportion of students who do their homework is 70%. Okay, so that would be changing the true value of P in the applet. What is the effect size? Well, the effect size is the difference between the true population proportion, which is 0.7, and the hypothesized, which is 0.5. So the effect size is that difference. So it's 20%. If I commit a type 2 error, let's say I commit a type 2 error, in context, what is my wrong conclusion? Well, recall that a type 2 error is failing to reject the null hypothesis when it's really false. So I'm saying, in this case, more than 50% do homework on Sunday, but my sample doesn't give enough evidence to show that. The power of the test is now 72%. Explain in context what that means. If 70% of the students actually wait until Sunday to do their homework, then there's a 72% probability that I will obtain a sample p-hat large enough to reject the null hypothesis. Okay, that's what the 72% power is telling me. Let's say the actual proportion of students who do their homework is really 55% instead of 70%. Compared to the situation in question 2, how will this affect my hypothesis test? Well, since 55% is so close to 50%, many sample proportions could plausibly have come from either distribution, so it's very difficult to get evidence that the null hypothesis is false. In other words, we're going to have a very high probability of a type 2 error and very low power on this test. Remember, effect size greatly affects power. Now, I changed the last question on the original notes here. How is it possible to detect a very small difference between the null hypothesis proportion and the actual proportion? So we've got a situation like this. How can I fix that? What change is very helpful? Well, I could increase the sample size. If I increase the sample size, notice in both of these, what I did, I made the true proportion 0.6 because I couldn't increase the sample size enough on the applet to make it a big enough difference with the 0.55. So these are fairly close together, still very difficult to detect a difference, lots of overlap in the distribution when the sample size is 30. But if I make the sample size 200, then I can see enough distinction between the two distributions that it would be more likely to detect the false null hypothesis. The power goes from 29% to 89% when I make this change. However, there is one problem with my particular situation. If n is equal to 200, 200 is not less than 10% of the CCHS student population. Okay, so I violated a condition. So that is a problem when you're dealing with proportions, that taking a large sample size is really helpful, but if you go too large, then you violate the 10% condition, and the probability calculations will be affected and they will not be accurate. So you do have to be careful about that.